Good evening everyone. So till now we have seen that how to write down the recurrence relation for a given problem. In today's class we will see how to solve the recurrence relation, in particular linear homogeneous recurrence relations. So if the recurrence relation has only two coefficients, for example an and an minus 1, then it is very easy to solve them. Either you use recursive backward substitution. For example, if you have the recurrence relation as an is equal to an minus 1 plus n, then you keep substituting the values of an minus 1. So an minus 1 is then an minus 2 plus n minus 1, and n is already there, and if you keep doing it you will realize that it will turn out to be, it goes till 1. Yes, so that is recursive backward substitution. Similarly, mathematical induction also works perfectly in these cases. For example, if I have to use mathematical induction to solve this recurrence relation, then first we need to identify the general term. To identify the general term, I can start with a2. So a2 is 2a1 plus 1, which is 3. Then a3, which is 2a2 plus 1, which is 7, and so on. So here you can observe that the general term might be 2 raised to the power n minus 1, but it need to be verified. I cannot claim it without proving it. So I have to use the mathematical induction. So for n is equal to 1, a1 is 2 raised to the power 1 minus 1, which is 1, which is correct. So let it is true for n minus 1, which means an minus 1 is 2 raised to the power n minus 1 minus 1, and I have to prove it, it is true for an. So an is given as 2an minus 1 plus 1, which is 2 times 2n minus 1 plus 1, and that turns out to be 2 raised to the power n minus 1. Hence, using mathematical induction, it is absolutely correct. But now the problem comes when there are more than one terms on the right hand side. So we will see how to solve these recurrence relation. So we start with linear recurrence relation. So we focused on the recurrence relation of this form, where c1, c2, cm are constants and g of n is a function of n. If g of n is 0, then we call it homogeneous recurrence relation. Otherwise, it is a non-homogeneous recurrence relation. So to proceed further, how to solve it, let us consider the following problem. an is equal to r an minus 1, where a naught is equal to k. What would be its solution? So its solution would be, if you try by yourself, you realize that an is k r raised to the power n. Yes. Now the important observation here is that for the recurrence relation, if I take the solution of the form r raised to the power n, and if I differentiate it, then it becomes n r raised to the power n minus 1. Next time r raised to the power n minus 2. So I have the terms in terms of an minus 1, an minus 2. So there looks a correspondence between them, and it works perfectly. Same as in the case of the differential equation with constant coefficient, where we used to assume the solution of the form e raised to the power mx. So here we will assume the solution of the form alpha raised to the power n. So we need to solve this recurrence relation, which is a homogeneous recurrence relation, and to solve it we will take the solution of the form alpha raised to the power n. So if I substitute alpha raised to the power n, then it becomes as follows. Now I can simplify it by reducing the power of alpha, and it becomes a polynomial of degree r. Or if I take the terms on one side, then we call it the characteristic equation. Now this characteristic equation would have the roots that gives us the different values of an. Once I have the different values of an, then their linear combination would also be a solution. That is very easy to verify. If there are 2 or 3 solutions, then their linear combination would also be a solution, and that gives us the general solution of the recurrence relation. Now using the initial conditions, I can easily find the particular values of these constants a1, a2, ar, capital A1, A2, ar, and that gives us the required solution for the recurrence relation. Things would be clear once we see some examples. So let us assume that we need to solve the following recurrence relation. So I start by assuming an is equal to alpha s to the power n. So recurrence relation becomes alpha s to the power n is 2 alpha s to the power n minus 1 plus 3 alpha s to the power n minus 2. So I can reduce the power of the alpha, and it turns out to be alpha square is 2 alpha plus 3. So that gives me a quadratic equation as follows. If you solve it, then alpha is 3n minus 1. It means my an is 3 raised to the power n and minus 1 raised to the power n. Or I can say the general solution is a1 3 raised to the power n plus minus 1 raised to the power n and a2. So this is the general solution. But with the initial conditions, I can easily find the value of capital A1, capital A2. So a naught is equal to 1 implies a1 plus a2 is equal to 1, and a1 is equal to 1 implies 3a1 minus a2 is equal to 1. If I solve them, then a1 is equal to half and a2 is equal to half. That means my required solution is half 3 raised to the power n plus half minus 1 raised to the power n. Okay, so very easy to solve this one. Let's see one more question. An is equal to an minus 1 plus an minus 2 with the initial condition. If you recall it, then it is the Fibonacci sequence, and if you solve it, then you will realize that you will get a quadratic equation in alpha whose roots are 1 plus root 5 by 2 and 1 minus root 5 by 2. So the general solution would look like this one, and if you use the initial condition, that gives you the values of a1 and a2. Yes. Now one quick observation is that in both the examples which we did, we got the distinct roots of the quadratic equation, but there may be possibility that we will get the equal roots or the repeated roots. So when we get the distinct roots of the quadratic equation, then we will get two linearly independent values for an, and we consider the linear combination. But in case of the repeated root, let's say I look for 3 linearly independent solutions, but because of the repeated root I may not get 3, because let's say I get the repeated root as 2, 2, 2. So I will get only 1, 2 raised to the power n. What would be the other one? I do not know, but I need 3 because there are 3 roots are there. So I need 3 linearly independent solutions. In case of differential equation, if one of the solution is, let's say, e raised to the power 2x, then the other solution used to be x e raised to the power 2x. Yes, the similar concept we will use here. So to begin with, let us consider the following problem. If you solve it, then you will realize that it would be alpha square minus 4 alpha plus 4 is equal to 0. That gives you alpha is equal to 2 comma 2. It means an is 2 raised to the power n. Yes. Now to need the other an, it cannot be the constant multiple of 2 raised to the power n, because if it is a constant multiple, then the general solution would have mainly 2 raised to the power n only. So it means the other solution should be a non-constant multiple of an, which means function of n multiplied by 2 raised to the power n. Now I need to find g of n. I should put it into the given recurrence relation. By putting it, I will get g n plus 2 and 2 raised to the power n plus 2 is equal to 4 gn plus 1 2 raised to the power n plus 1 minus 4 gn 2 raised to the power. If I cancel out 2 raised to the power n and there is one 4 common, then it turns out to be gn plus 2 is 2 gn plus 1 minus g of n. And it's very easy to see here that g of n is equal to n satisfies the equation 1, which means my required solution an is n 2 raised to the power n, and therefore the general solution is c1 2 raised to the power n plus c2 n 2 raised to the power n. Then I use the initial conditions, which are a0 is equal to 1 and a1 is equal to 3, and if you solve it, then an comes out to be 2 raised to the power n plus n 2 raised to the power n minus 1. Yes. So the quick observation is that if R is a characteristic root with multiplicity j, then r raised to the power n is a solution, n r raised to the power n, and till n raised to the power j minus 1 r raised to the power n, all would be the solutions of the recurrence relation. Yes, let's try one more question. So solve the following recurrence relation with the initial conditions. Please do try by yourself. You will observe here that alpha comes out to be 3, 3. Yes, it means my general solution is an is equal to c1 3 raised to the power n plus c2 n 3 raised to the power n. And if you solve it, then after solving it, you will get c1 as 1 and c2 as 1 by 3. That gives me an as 3 raised to the power n plus n 3 raised to the power n minus 1. Okay, let's try one more question. So we have considered two cases, distinct roots or repeated root. The last case is the complex root. So to understand, let us see the following question. Here again, the characteristic equation comes out to be alpha raised to the power 4 plus 2 alpha square plus 1 is equal to 0. That gives you alpha square plus 1 whole square is equal to 1, or alpha is equal to plus minus I, repeated roots. It means an would be a1 I raised to the power n plus a2 n I raised to the power n plus a3 minus I raised to the power n plus a4 n minus I raised to the power n. Now using the initial conditions, I can easily find the values of a1, a2, a3, a4, and that gives me the required answer. In the next class, we will see how do we solve the non-homogeneous recurrence relation.